So what we did last couple times, started at the cochlear nuclei. You've got these cells that are phase locked, so they respond to the sound pressure wave peaks, or they detect the amplitude, and they kind of ignore the phase locking. That's the first stream. And then it goes into the nucleus laminaris, where it does a comparison between the left and the right ear. And so if we just make a quick and dirty drawing up here of the things we talked about. So we talked about here's the pons midbrain junction. We come into the nucleus magnocellularus, and then that projects to this big, there's another one on this side. There's the midline. So this guy is the NM, and this guy is NL for nucleus laminaris. And there's another NM on the other side that breaks the rule of Serino and comes over NM. So this guy comes over, goes through the nucleus that way. This guy comes over, goes through the nucleus that way. And then we have these coincidence detectors. They detect where in the nucleus, going through the nucleus, perpendicular to frequency. So this is frequency this way, where that coincidence occurred. And so what we're talking about today is we project those guys up to the inferior colliculus. And so here's the inferior colliculus, and it's got this external part. So this guy was the inferior colliculus external, and then it had a inferior colliculus central nucleus lateral part, and then we also had an inferior colliculus central nucleus medial part. And what do those projections look like? Well, they come out of here, and they go up there, and then we also had some amplitude projections. I'll leave them out of the diagram for now, but we're going to start off with just this projection right here that goes from the lateral part into the external part. And when we look at the response coming out of the nucleus laminaris, if we look at the response as a function of interaural time difference, we had this picture that looked like something like this. So if this is 0 microseconds, ITD, interaural time difference, what we found is that a given neuron might, respond something like this. So it gives an ambiguous response. It will give a response that's big to, say, 150, and a response that's big to 10, and then a response that's big to, say, 130, minus 130. So this neuron can't tell whether is the object like right in the front, or is it, off to the right where it got to the right ear first, or is it off to the left where it got to the left ear first? So this is ambiguous response. And what does this come from? It just comes from the nucleus laminaris just matching every spike. So there's a train of spikes that comes down, and it just matches all of them. And so it'll accidentally match like the first spike with the second hump coming out of the other ear, or the third hump coming out of the other ear. So what we did is we then said, well, here's another neuron, and that other neuron actually has a different set of ambiguities, like that. So this is neuron 1. And then here's, never think ahead, got to think ahead a little bit more. So here's neuron 1, number 1. And then this guy is ambiguous also. It says it might be these different interoral time differences. And so that's neuron 2. So neuron 2 is also ambiguous, but it has a different ambiguity. So this is neuron number 2, different ambiguity. So what are we doing there? So what we're doing there is we're looking at one neuron, many ITDs, okay? This is all, like I said at the beginning, we always have to reduce everything down to a two-dimension. We only got like, two useful dimensions to work with. It's already hard to deal with depth. So that's one neuron and many ITDs. So one dimension is ITD, the other dimension is the response, and then we can put two neurons at most on our graph and sort of get an idea of how different single neurons respond to many different ITDs. And so now what we want to do is kind of switch gears and look at the converse thing, which is, since we know that the neurons respond this way, what does it look like across the entire nucleus? So if we go across the entire nucleus and just play one ITD, so it's kind of the converse picture. So this is one ITD, one interoral time difference. So say, what does that mean? That means like in practice, we take a sound, here's a sound like that, and this is, the left ear. And if we want to do it very exactly, what we'll do is we'll just digitally shift that sound in time and play it into the owl headphones. Here's the right ear. And so say we'll shift it by 150 microseconds. So this is, this might be, ITD, for example, 150 microseconds. So that's about a tenth of a sixth of a millisecond, a sixth of a thousandth of a second. And then now let's look at all the neurons in the nuclei. Now that's hard to do sort of if you're actually trying to record, because how could you record from like 10,000 places in the nucleus at once? You would damage the nucleus beyond repair. But what we can do is we can record from a couple places and sort of interpolate in between, and just to get some picture of what happens when we just play a single ITD. And what's going to happen is you're going to get some ambiguous responses, but the ambiguous responses look a little different. So let's draw out just two different ITDs. So here we had two neurons. So we had two neurons, many ITDs. Two neurons, many ITDs. And so what we could do now is just do two ITDs many neurons, okay? So that's kind of the other way of looking at it. Let's just look at what does the spatial pattern look across the entire nucleus if we just played one ITD. And now let's change to just one other ITD. Now what does the spatial pattern look across all the neurons? So two neurons, many ITDs. This is two ITDs, many neurons. So it's a conceptually, confusingly different picture. So if we plot out what happens make sure I leave enough space for my space map. Okay, so should be good. So this is, so this would be what happens in the nucleus laminaris, but it's very similar to, I'll explain why that is. It's very similar to what happens in the ICc lateral. So you get a similar picture. So what are the coordinates here of our two-dimensional map? So we got frequency here, and we got characteristic delay going this way. And so so frequency running up this way, characteristic delay going across the nucleus. So if we just play one frequency in, what's going to happen? You're going to end up with potentially multiple spots in the nucleus. Now it's a little conceptually confusing, but just work this out. So here we had just one neuron, and right here is the one neuron, say the dashed one. We played all these different ITDs, and we got two different peaks of response. What does that imply if we looked at a bunch of these neurons across the nucleus? It implies that more than one neuron across the nucleus is going to be active for one ITD. It's the inverse. So this is a bunch of ITDs, one neuron. You show multiple peaks where there's a big response. Now let's look at a whole bunch of neurons with different characteristic delays. The implication is you're going to get multiple neurons at different points in the nucleus that respond to one ITD. Now, if we only have one pitch, we can't tell, like is the object over here? Is that the real delay, or is that the real delay? I can't tell. And so what we need to do is, if frequency is going up this way, we need to have some other pitches in there. And so we said if you just play a pure pitch, you can't tell where it is. You can tell something about it. You can say, I know it's either here or here or here, but you can't tell which one of those it is. So you've done something. And that pretty much corresponds to like the response that you see in the nucleus laminaris or in the inferior colliculus central nucleus lateral part. It's ambiguous. You don't know, is it that one or that one? I can't tell because I only got one frequency. But if we have another frequency, so say we have a higher frequency, you might get something that looks like this. And the peaks are closer to each other in characteristic delay, which makes sense because it's a higher frequency sound, and so that means the same amount of ITD. The ambiguous peaks are going to be closer to each other because the spacing between those peaks is basically equivalent to the spacing. It's caused by this spacing between the successive sound waves that we're matching between the left and the right ear. And if you do a lower frequency is going to have an even more spread out peaks. And if we do a whole bunch of frequencies, you'll get something across the nucleus that kind of looks something like this. So you get these little stripes across the nucleus, and they'll get closer. The stripes will get closer to each other as you go up in frequency. So you can sort of see how you solve the problem now. This is kind of like the aperture problem. So if you play a second ITD, so that's neuron 1, neuron 2. Now this is ITD number 1 and ITD number 2. So if you play a second ITD, you'll get a different pattern which might look something like this. So there'll be stripes across the nucleus, but the stripes are going to move, just like the characteristic delays would move. And so you'll get something that kind of looks, the stripes will be closer spaced at the high frequency end. Right, this is still frequency, the high frequency end of the nucleus. And so how do you solve the problem? Well, if we just sum across all the different frequencies, then you can see if we sum across this column. Oh man, need another color for that. So if we sum across that column, we're going to get a big sum. If we sum across this column, we'll get a smaller sum. And then if we go to this picture, if we sum across that same column over here, we'll get something, but we'll get a bigger number if we sum across here. So this is, big sum, small sum, and now we got big sum and small sum. So that's this suggestion for how we solve this problem. We look across frequency, and so sum across frequency, and then we just find out which sum across all the different frequencies, all the different characteristic delays, across all the different characteristic delays is the biggest. And then that one is going to be the actual true delay, the actual sort of real interaural time delay. So basically the bottom line is, this is true characteristic delay. Delay, equals ITD. That's the actual ITD. So you might wonder, how do you do that? And one way of doing it is you just get some rogue auditory cortical neurons. So what do auditory cortical neurons do? Well, normally what they do is they take a little plane of neurons. So this is, tono is going that way. That's the tonotopic gradient across this nucleus. So they take a little, plane of neurons there, and all the neurons in that plane project typically to another plane in the next nucleus. Now, under normal circumstances, the way you do this is you actually respect the tonotopy in the other nucleus. And so under normal circumstances, for most parts of the auditory system, you just go to a plane that's at the same tonotopic. So here's the second nucleus. There's tono, running in that direction across the nucleus. And so normally what you would do is you would just say, each neuron over here goes here, and it just projects to this plane. And then we've got another tonotopic map. The tonotopic map is running this way. So how do we do this? Well, you just need some rogue neurons that say we are not going to do that. What we're going to do is we're going to take this neuron and we're going to basically project to a different plane. So you could just project, let's just all go to this plane instead, and get neurons that come from different planes over here, all going to one plane over here. So you just got to get some rogue neurons. So here's another plane. So here's the plane that's at this end. And get all these guys together and just project to this plane. So you're still sort of doing plane to, point to plane, but you've just decided we're going to all sort of go to this other plane, sort of rotate. You could also think of it as kind of like rotating your projection plane. So since you've already got neurons that kind of spread out across a plane, it's not too hard to just imagine some rogue neurons deciding to just sum across the columns. And there's anatomical evidence that that's actually what happens. So as we'll see when you get to the space map over here, you can see that if you inject a tiny bit of the space map, you can see you're getting input from a plane of neurons in the ICC lateral that are representing different frequencies. So what? How can we make a space map? So this only made one dimension of our map. And before I talk about that, I would just mention, the space map is over here in the ICX, but what happens? What's the difference between the nucleus laminaris and the ICC lateral? They're kind of the same. This could be a drawing of either the nucleus laminaris or the ICC lateral. So what's going on is that this is kind of the first high performance station where we want to do the matching. So you could have immediately gone from nucleus laminaris up to the space map, but nucleus laminaris doesn't want to sort of let's not confuse things, and so let's just sort of do our high performance matching and then send the information to nucleus ICC lateral, and then let ICC lateral figure out how to do the rogue auditory thing and sum across frequency. And so if you look at the representation in ICC lateral, it's kind of similar. It's kind of similar to the representation in nucleus laminaris. There's frequency going in one direction, and there's characteristic delay going the other direction. Now, notice, in order to get that, the projection from ICC, from nucleus laminaris must have been, more or less point to point. So it also has to do a little bit of a rogue thing here, where it instead of doing point to plane, it's got to do more of a point to point or point to line type projection. If we do it in 3D, because all these structures are actually little cubes here. They're little cubes, and so in order to get separate neurons that respond to a particular characteristic delay, particular frequency, you must have done something more like a point-to-line projection, but that's a little fine point there. But the end result is you end up with a representation in inferior colliculus, central nucleus lateral part that looks pretty much the same as the representation in the nucleus laminaris. You've got frequency going in one direction and characteristic delay going in the other direction. Okay, so now how do we actually make a space map out of this? So we've got our rogue neurons that the space map is smaller than the ICC lateral, but I'm going to make a giant one so that I can. So here's a massive ICX. So this guy's ICX. Yeah. I wonder, I do that all the time. It's just like my brain is. Okay. So here's our ICX. Make a nice perspective one. Yeah. So it's a little cube of all parts of the neurons look like little cubes of cheese. Okay, so here's our ICX. So this is like a little. Okay, there we go. So how do we make a space map? So there's two dimensions to the space map. So now we're just going to start off with one dimension, and that dimension, if you read in the literature, it will be called azimuth, and that's just basically the x direction, horizontal direction. So basically what we want for our space map is we want to have, azimuth running across the space map in this direction. There we go. So how do we do that? So what we need to do is we need to basically get all the neurons in this column and have them project to a plane over here. So we still need a plane. So if you look at the projection, this projection, it still looks like a point-to-plane type projection. So what color do we need? So what we're going to do is we're going to project to a plane over here. So here's that plane. So it's a plane in this nucleus, ICx nucleus. Man, I didn't do my perspective right. There's got to be a parallel there. There we go, it's more or less right. Okay, so there's that plane there. And so what we want to do is I'll do this one, it's closer. Okay, so I'll do this one. So we want to get all the neurons in this nucleus, and I'll do this one. All the neurons in this nucleus, and want to take them out and get all the ones from different frequencies. So, all freaks. So get all frequencies, and then project them into this plane. So if you didn't know any better, you would say, this looks like a regular point-to-plane projection. Auditory system knows how to do that. So, all frequencies, 1 characteristic delay. So all frequencies, sum across all frequencies, and just get one characteristic delay. Okay, so now, what do we do for other characteristic delays? Just project those to other planes. So let's put another one back up here. So here's another one that goes down there. Don't crud up the diagram too much. Okay, so that's a separate characteristic delay. So that's a different one. So a different column would project over here like that. This is different column from ICc lateral. So now what do we have? So now we've got a map of X position. We have a map of X position. We don't have there's no Y position in it. It's not responding to the Y position. But if we place sounds at different X positions, they go to different parts of this nucleus. So we have the beginnings of a space map. Okay, so let's just stop there for a second and see if we have any questions. So all we've done is we did the coincidence detection here, and the coincidence detection spread out this second dimension, which was the characteristic delay, and then we more or less did a point-to-point projection of this guy up to point-to-line type projection up to ICc lateral, and that just duplicated the response that we already have in the ICc lateral, that we already have in the nucleus laminaris in ICc lateral. If you do experiments in ICc lateral, it looks just like nucleus laminaris. You get multiple peaks if you change the ITD, and when you go to different parts of the nucleus, you can see the ambiguity shifts around. So we did our coincidence detection in nucleus laminaris, more or less just sent that along without really doing much to it to ICC lateral. And then we had these rogue neurons that said, like, let's just like sum across frequency instead of summing across one frequency. So so those guys, they now, all the neurons coming from from basically a plane here. So here's that characteristic delay plane. So all the neurons go to another plane over here. And so now what we have is a map of space. So if you play a sound, it has to contain multiple frequencies for this to work. So because if we just played in one frequency, there'd be two spots. If we just had a single frequency, there'd be two spots in the nucleus, and there'd be two planes, and you couldn't tell which plane was the correct one. So we need to have multiple frequencies, at least two, but like 10 or 20 would be even better across different frequencies. So, a sound that's very easy to localize, like a shh kind of sound, very easy to localize because it has multiple frequencies. And so what that will do is that will give us our x-axis. So how do we get the y-axis? So the y-axis comes because of owls, because of this strange thing that barn owls have developed, which is they've got sort of these big eyes. There's a big barn owl eye. And business end right here. The beak. But if you actually look at their ears are kind of forward, and they've got this radar dish of very hard feathers that slightly point up on one ear, but the other ear slightly points down. So here's the radar dish on the other ear. And so what does that do? That makes an interaural intensity difference between the ears. So normally if your ears aren't tweaked, what will happen is if a sound is on the right, it's louder in the right ear. Sound is on the left, it's louder in the left ear. But if you've got your ears tweaked like this, now a sound that's on the left of the owl, if it's a high sound, it's going to be louder in the right, in the owl's left ear, and softer in the owl's right ear. And so we've got to do some work, which I didn't describe. So we have to calculate. The first thing we have to do is calculate the amplitude in each ear, but then you have to calculate the IID. So that's the interaural intensity difference. And there's another nucleus that does that. That's there's like these two nuclei sort of sitting right here. Let me get there's the pons midbrain junction just below them. And those nuclei were the VLVA, and this guy was VLVP. And the VLVP one is the so this guy is time, the anterior one, and this guy is amplitude. And those are both binaural nuclei, so that means they're doing this calculation. So calculation ID, ID, and so we think this is in difference in VLVP, the posterior one, and then also the ICc medial. So this guy is going to go up to ICc medial, and then ICc medial is going to go over to the ICX also. That's what I'm going to draw over here. So I always, if you look at the human ears aren't tweaked. And so enterprising auditory psychophysicists have said, why do we make some undergraduates walk around campus with a special hat on that sort of looks like this? It's got like a little blocker for the one ear like that, so that ear can't hear from up, and then another blocker with this ear, so that this ear can't hear from down. So we'll turn them into an owl. Make them walk around campus for a month or so to get used to it, and then check out, can they actually sort of, in the dark, tell up and down? And yes, sure enough, if you give them some owl ears, they can do it. But the owl has worked it out so that if you've got a nice big amplitude difference between the left and the right ear as a function of elevation, now we've got the second dimension. And so how does that work? Well, if we take this ICc medial part. So here's VLVA, VLPP, sorry. So this guy, this is eventually getting input from nucleus angularis. So nucleus angularis goes here, but then we get the other nucleus angularis, from the other side is also going here because there's a binaural nucleus. So there's the other NA. This is binaural, just like nucleus laminaris is. And then that projects here. And now if we do the same rogue thing where we collect all frequencies, but one characteristic amplitude difference. So here we're just looking, we don't care about frequency anymore, we just want the amplitude difference. So basically, collect all frequencies for one amplitude difference. And now we're going to send that into this nucleus, but we're going to send it into a plane going this way. Like that. So send it into a plane, a horizontal plane in the nucleus. And this has actually been, amazingly, this has been worked out anatomically by injecting tracers into ICX and seeing where they go, what frequencies do they go to. So if we take all these guys and now do our regular point-to-plane projection, but we've got to tweak it to sort of go, perpendicular to the other plane. What's going to happen? What's going to happen is right where they intersect. So here's a little chunk where they intersect, right there. There's going to be a response an input from both planes. So both of these planes are going to provide an input at that point. And so basically right where they intersect, the neurons are going to be most excited. And so the end result is we'll end up with a two-dimensional space map. So we'll end up with a two-dimensional space map because if you look at this nucleus, what's going to happen is this is going to represent elevation. Because what is elevation? Well, elevation is just basically how loud was it in each ear? What's the loudness difference? So if it's really loud in the owl's left ear, that means it's pretty high. If it's sort of about the same loudness in the left and the right, that means it's kind of in the middle. And if it's really loud in the owl's right ear, then it's going to mean it's down. And so if you record I mean, so what's the history of this? They knew that something like this was going on because they started off recording in the owl's forebrain, and then they found that there were neurons like this. And what does like this means? Well, say we just play a sound that contains a lot of frequencies and vary the azimuth of the sound and the elevation. So elevation that way, azimuth this way. What you find for a particular neuron in ICX, this is ICX neuron. If you play different frequencies, it doesn't care. It gives a response to many different frequencies. But you'll find for a particular elevation, there'll be like a big response, and for a particular azimuth. So we already knew, 30 years ago, that different forebrain neurons did this. And so what several people did, particularly Mark Kanishi, they said, well, let's just go down to the brainstem and figure out where it's happening. And so where it's happening is in this ICX nucleus, because the same thing happens from the ICX. And then what happens after that is we take those point-to-point projections and just project them to the superior colliculus. And why do we do that? Well, what is the whole goal here? The whole goal is to eat the mouse. And so the superior colliculus is the part of the brain. So this is kind of like we just do point to line to the superior colliculus. So there's a visual map in the superior colliculus, and we just project this constructed auditory map onto it, with our, point to line type projections. We're going into the visual system, and so we got to do like the visual system guys do, and just do point to line. And so now we're point to point. And so now what happens is in complete darkness, a little sound can happen someplace. The owl can localize it by summing across frequencies in interaural time delay and amplitude, and then essentially figure out where it is, send that to the colliculus, and the colliculus can direct the head to nail the mouse. So that's the amazing story of the space map, how to construct a map out of space, construct a map of space out of signals that are just the different frequencies coming into the left and the right ear. It's an amazing story. Now, you might think, yeah, okay, but that's just owls eating mice. We're in the cognitive science department. We're trying to sort of figure out how higher level things work. Is this relevant? Is this relevant at all to us? And it turns out, yes, it definitely is relevant. And so if we look at the connections, so we got nucleus laminaris here, and that goes up to, ICc lateral, and that goes up to ICX, and we make a space map there. And then once we got that space map, we project it to the superior colliculus. But that's not the only thing that goes on. So there's also a projection from the ICC lateral, a bigger projection than the one that goes to ICX, much bigger, so make that bigger. So this bigger projection is going to, we got to make it go a little further. It goes up to the medial geniculate nucleus. And then this thing goes up to the cortex. That's a much bigger projection actually than the one that goes to the space map. So how could we use this tricky construction of a space map business? And if we think about it, what is the ICC lateral done? What it's done is it's sorted things by space. So this is characteristic delay going in this direction, but that's really space. Once we've sort of like summed across frequency, that basically corresponds to actual x dimension space. So that's more or less like x dimension space. So we've sorted things by space, but one thing we can do is we can sum across all the frequencies and blot out any difference in the response as a function of frequency, or what we could do is we could just save it. So what's going to happen if you're in sort of a loud pub with people yelling in your ear and you're trying to talk to somebody? So you're sitting in there. There's some drunken guy over here that's yelling in your ear, but you're actually trying to talk to this person over here. You want to somehow filter him out. So how do we filter out that signal, which might be louder than the person you're talking to, and concentrate on this person? So what we could do, since we know that person I'm talking to is more or less in this characteristic delay column, let's just shut down the other characteristic delay columns. So if we just inhibit all the other characteristic delay, somebody else has to do this, but say we just inhibit this guy. Inhibit this one. What's going to come through? So what's present at each of these places? Well, you could sort of think what's present is a spectrum. So there's some, if this is frequency, there's some low frequencies, and maybe here's the person's voice, and here's some of their, S's, and then here's the band playing, the symbols of the band playing in the background. There's a spectrum because we've sorted by frequency. So this is a spectrum of different frequencies. And what's going to happen? Well, here's the guy that's making noise. He's got his own spectrum and his own information. And what we want to do is just blot that out. And so then what happens is now we still have all the frequency information. Frequency is preserved. And we can send it up to the cortex to try to sort of understand what the person is saying. So we don't just use it to construct a space map to eat mice. So the same thing is extremely valuable for essentially filtering sounds by where they're coming from. And if you lose one ear, one of the first things that people will complain about is, I really have trouble understanding what's going on when there's multiple people talking. It's really hard to sort of hear what's going on when there's multiple people talking, because you've gotten rid of this sorting mechanism that uses space to sort frequencies, but then doesn't collapse across frequencies. Instead, you preserve all the information about all the things that person is saying and send it up to the cortex. So the bottom line is that this kind of method of spatializing the characteristic delay, which is basically done by the nucleus laminaris. The nucleus laminaris is the one that really does it by doing these delay lines, is highly useful, not just for SpaceMap, but it can be useful for auditory attention. So auditory, spatial attention, and that's critical for trying to. It's like the barn owl. It's critical for making sense of what people are saying in a bar, but it's critical for essentially allowing you to focus your auditory attention on a particular spot, and then send that stream of auditory information up to the higher level analysis pathways without smearing it out across frequency. Okay, so any questions in the last negative 2 minutes about this? So starting at the ICC, starting at nucleus magnocellularis, laminaris, up to the ICC, go to ICX. So any space map, did this make sense over here? That this idea how if we basically kind of suppress all the information coming from this part of the nucleus, then what we've done is we're just letting through. So all these frequencies overlap, So this, this guy, the guy is yelling. Maybe it's like a big frequency there. So that's the same frequency as this guy. But what we've done is we've peeled that out and got rid of that signal and allowed us to listen to this softer signal, which has the same frequency in it, so that we can figure out what the person you're talking to is saying. So it's just the way that the brain plays around with maps. So you have visual maps, and those seem low level because it's just the retina projecting to different parts of the lateral geniculate. But the brain does all different kinds of things with maps. And so it's just messing, this is the auditory system just messing around with maps and essentially spreading out the signal across a two-dimensional map. And then once you've got it spread out, we can sort of do other little tricky things to it, like suppress signals that are overlapping signals that are coming from different points in space, and just concentrate on one point in space. Okay, I can hear the stunned silence out there. It's got to be one little little question. Any questions out there? All clear? I got so far ahead that everybody got completely lost? No. All good. Keep freak. Keep freaks, and this is, sum across freaks. We do the same thing as the owls. We also need to be able to look at something that we heard. So if a little sound in the dark happens, you want to be able to use your superior colliculus to look at where did that sound come from. So it's not like we don't do this. We definitely do the same thing. We also sum across frequencies, but in addition, another part of the system keeps all the frequencies so that we can do some higher level analysis and figure out what was said. Okay, any little questions? We can all rewind to the very beginning. All good on the space map. This is the ICx-SpaceMap. It's amazing if you look anatomically at these structures, they hardly look any different. If you just anatomically look, the ICC medial looks almost the same as the ICC lateral. You can barely see the difference. And when you go into the ICX, it's a small little thing off to the side. It actually doesn't look like much. And this was all figured out by recording in different parts of it. So, and almost all this stuff is coming from, these initial delay lines. So you only have to do the delay lines once. So you do this like high performance delay lines, and then once you've got stuff spread out in characteristic delay, then you can sort of mess around with it in various ways. Okay, one last call. Any small question? Okay, well, I guess we'll end the recording there.